So we are basically interested in learning basics of nuclear magnetic resonance. So we'll first try to do various, so what's the classical picture that one has of this, then what's the quantum mechanical picture, and what is the phenomena, what kind of information it gives, and we'll go on in that manner. So we are obviously interested in nuclei which have a magnetic moment. You're all aware nuclei contain protons, neutrons. Each has a magnetic moment. Overall, they have some spin angular momentum, and in those cases, you can do this resonance experiment. So, just some initial notations, right? So, you have a nuclear magnetic moment, okay, which we call mu, okay, and there is a nuclear, again, angular momentum, which we call J, right? So how are mu and J related to each other? In general, they are proportional and opposite and all. Maybe it depends on the sign of the charge, etc. But what is the proportionality constant called? So it's called gyromagnetic ratio. You have a, in general, need not be nuclei. In general, if you have a magnetic moment and then there's also an associated angular momentum, spin angular momentum, then they are related to each other by a factor gamma, which goes by the name of a gyromagnetic ratio. Further, again, just still notation. So this J angular momentum is in units of h bar, and our convention is usually write it as h bar times, for nuclei you put angular momentum operator I. Okay, that is the notation. For electrons and all, you might put again J or a S, varies. So for nuclei, it's I. So what we really have, you can connect the magnetic moment to the nuclear angular momentum operator I. Okay, so overall we have a gamma h bar factor which connects mu to I. Okay, and so then when you do a quantum mechanical treatment, you will deal with this I, right? So you will deal with I square, IZ, and so on. Okay, so you have done in some courses this kind of angular momentum algebra, right? So we'll use some of it. So you can do expectation value of these things, right? So this, you know what it is, right? This is I times I plus 1, right? Likewise, if you, so you can do expectation value of Iz. So this is again, so again notation. So you can write that as m sub I. So with the spin half, you can have plus half or minus half. So those are the possible values of the expectation value of Iz. Similarly, you can write I times I plus 1. Also, some things we'll use at some point. So I square and Iz commute with each other. Okay, in quantum mechanics, you know what this means when they commute with each other.
Simultaneous measurements.
So you You can find simultaneous eigenvalues. Okay. So you know the operation one has to do, and so one, for example, we'll write it like this. You're also familiar that Ix, so x component, y component, z component, Ix and Iy, so any two components, they don't commute, right? And they're also connected by this cyclic manner. Ix, Iy is to Iz and so on. Okay. So if, for example, we want to write a state expectation value of some Ix, okay, mu x rather, so or just the operators for some magnetic moment x component, then this can be written in terms of, so you know angular momentum algebra in terms of what are the expectation values of various I operators and so on. In terms of an observable, you are looking at the magnetic moment, but we know you can connect the magnetic moment to the angular momentum via gamma h bar, right? So one can just replace this by gamma h bar Ix prime, and then the matrix elements of various angular momenta, there are rules to determine those. Okay, so that's how one would go. So by the way, should mention, so what, there's a lot of literature, a lot of textbooks and all available on these topics. So one well known is so it's by Slichter. So Fundamentals of NMR or something, title is, I forget the title. So the book by Slichter and another one by Abraham, which are standard textbooks for nuclear magnetic resonance. Okay, so almost all the material will be following this. Then there are these are sort of old ones. These are like Ashcroft, Merman, Kittel for solid state physics. These are for NMR. Then there are more recent ones. So one very practical one is called nuts and bolts of NMR. So actually, what do? You know, you have a spectrometer, you have a magnet. How do you put the sample? What do you actually measure? What do you vary? More in terms of, you know, you don't do operators and all. No? In a lab, you cannot be measuring some operator. You're actually having some circuit, you're applying some current or voltage and field and all, and then you're measuring something. So what are you actually doing to actually get insight into these things? So there's such a book called Nuts and Bolts of NMR. So this is Fukushima and Roder. And then there are now many others also. If I remember right, is that the author? There's one by
spin dynamic M.
Cohen, or there's one by Levitt also. So I'll look at the precise names and.
Levitt.
There's one by Levitt, there's one by Cohen. So these are all usually this thick. You don't need to read the full book for getting an insight. One has to focus on some specific chapters because a lot of it might refer to. So NMR, you generally learn that chemists use it. Okay. Not very often you see physicists trying to use it. So chemists, biologists use it. So chemists basically use it to look at what the local environment is, how it changes in different organic compounds, inorganic compounds, and so on. So I'll talk about that at some point. Our focus is really on magnetic properties. And how do you get insight into magnetic properties? By this local probe technique. Okay. So anyway, so Slichter and Abraham are standard texts. And then there are these others which are also very useful. Right, so properties of a system based on this matrix elements and all can be obtained in this manner. So let's just first consider a very simple quantum mechanical description of the resonance phenomenon. So, if you have a magnetic moment mu, okay, and if you place it in a field H, okay, then what is the Hamiltonian governing? Yeah, you have a magnetic moment mu in an applied magnetic field H. So, what is the Hamiltonian which governs this now? Right? Which will give you the energy, no? So, it's mu dot H minus mu dot H. It's similar to electric dipoles in an electric field, right? Minus P dot E. So similarly, magnetic dipoles in a magnetic field. So this is what you would write classically. So in quantum mechanically, you would write the Hamiltonian like this and then put suitable operators for mu, which we know now. Okay, gamma h bar I dot H. That's the relevant Hamiltonian term. Right. So your H for this case is minus gamma h bar, and let's say we are dealing with, we choose constant magnetic field, spatially uniform magnetic field, and we choose that as the z direction. So this is just gamma h bar h naught I z. So that's my Hamiltonian. Okay. And let's next consider just a simple spin 3/2 nucleus. Okay. So spin 3/2 nucleus. Okay. So we are aware. So because of this dot product here, we have a mu z dot. So mu dot h. So mu z, and there's only a z component. So therefore a mu z h naught. And so therefore gamma h bar I z h naught. So that's my total Hamiltonian. And so if you want to know the energy levels, it's straightforward now. You want the expectation value, so you just need the expectation value of I z. So for spin 3/2 you have 3/2 half minus half minus 3/2, and the energy level scheme is going to be exactly that. Because of the minus sign, the plus 3/2 will be the lowest, and then so on. Right, so for spin 3/2, you'll have m sub I minus 3/2 lowest, m sub I minus, plus 3/2 lowest, plus half next, then minus half, and minus. And of course, these spacings are all equal, right? That's the way Hamiltonian is. So if you now want to cause transitions between these, you need to apply a field where there's a frequency, right? And then you must match h bar omega to this energy level difference. Energy level difference is known. Okay, you just calculate the energy for the 3/2, calculate energy for the half. Difference of that is straightforward, right? Here. You have it here. So you take expectation value, there'll be a 3/2, and then on a half, so 3/2 minus half, right? So 1. Yeah. So gamma h bar h naught. That's the energy level spacing.
And to to splitting this, finally we need some kind of order of Tesla magnitude of magnetic field to have some nuclear level of splitting.
So you're asking what's the value of the field we can have?
Roughly.
In principle, anything. This is the nuclear Zeeman effect. The moment you have a DC field, you get a splitting. Your question is maybe deeper. In actual practice, is it okay to have just 10 Gauss and do a measurement? So we'll come to that. So usually not. There are practical sort of problems. Okay, what determines your size of the signal?
But splitting is happening. Even
The moment you have the fact that you have an H naught non-zero means you have a splitting. Once you have a splitting, you can cause resonance. You need H bar omega which matches this gamma H bar H naught, and that's resonance. In practice, what is the size of the signal that you get? Fukushima rotor, the nuts and bolts. That will help, but we'll talk about that. In practice, can one apply a field of just 100 Gauss and get a resonance? So we're digressing a bit, but in a lab scale like this, usually you need fields of Tesla or so more. But remember, you can, in principle, it's done in practice also. You can design electronics and probes where you do very fine measurements also. Okay, so even in small fields. I mean, it's just an in principle issue, right? So suppose Tesla field is giving some electronic signal of volts. Okay, then if you have millitesla, then it will give millivolts. I mean, just loosely speaking. So even smaller will give maybe microvolt. We just need some good detection mechanism which can amplify that. So it's not impossible. Squid, you're familiar with squid devices. They have very great sensitivity to magnetic fields.
And according to that, which part of radiation we have to be resonance with that particular signal, which will be accepted.
So issue is what is the value of the field that you apply, so that your electronics can deal with the signal generated which are of some measurable value. So, but you can in principle have very sensitive electronics which can detect even smaller and smaller. It's not impossible. I mean, in the squid magnetometer you detect flux quantum, one flux quantum in principle, which is very, very small. So you can detect very small magnetic fields. Likewise, it's not impossible, it can be done, but typically in a lab, you have fields of like a Tesla. And again, in advance, I'll tell you, the signal generated in an NMR experiment is higher when the field is higher. So everybody wants as high a field as possible. Okay. So in the institute, the highest field that is available, this kind of fixed field NMR, is about 15 Tesla. So it's 750 megahertz of proton resonance. Proton has 40 some megahertz per Tesla, so it's like 16 Tesla, in the neighborhood of 16 Tesla.
Inside.
So that would be usually biological samples.
Here we are focusing on nucleus, but magnetism will be because of electrons.
Right. So we come to that. So we are looking at a phenomenon which involves nuclei, but our focus is not really on nuclei themselves. We want them as an indirect probe of something else. And our focus, what we have in our mind is we want to probe magnetism in materials. Magnetism is arising from the electrons. So how this now can detect what's happening with the electrons? That's the rest of the thing. So you get these levels, and of course they're equally spaced. And in order to cause excitations, transitions from one level to another, you need another field, AC field, and one can give arguments. You need it to be perpendicular to the K direction. Your DC field is in Z direction, K direction. Any other field, firstly you need this equals H bar omega, where omega is the angular frequency corresponding to the AC field that you're going to apply now. That needs to be in the XY plane. Okay. Any transitions between these levels, it requires a transverse field. You can give all kinds of arguments. If you have, right? So if you have operator with just again an edge, you cannot change the m sub I for that, right? If you have if you have a raising or lowering operator, okay, that can change from plus half to minus half or 3 half to half, right? So it's only Ix or Iy which can be, right? So ultimately, again, bit in advance, you're going to now involve also AC field in this. So then you will need to, if the AC field has only a Z component, then you will have only mu Z. So eventually just Iz. But Iz acting on 3 half will give something times 3 half. So it doesn't change this state. It's only if you have mu x or mu y, right? Then that state can get changed. You understand how? You've done atomic physics. So somebody has idea? We do that shortly, but
L plus and L minus log
yeah.
that operator and changing the state.
Yeah. So if you have x, if you have mu x or ix, then again in terms of the algebra, ix can be written in terms of I plus and I minus,
Yes.
right? So I plus is in terms of x and y. What is it? Ix plus iy. That I is equal to minus 1, and I minus is ix minus iyy. So the mu x can be written as a ix, which can be written in terms of I plus and I minus. So if now I plus and I minus act on some of these, then it is possible to change. I plus acting on plus half will change it to minus, and so on. Okay. So you need transverse component of the field to cause transition. The longitudinal component simply changes the energy level spacing, nothing else. To cause transitions, you need a transverse component. Okay. So let's say we have some perturbation which looks like perturbing Hamiltonian through a transverse field. So which looks like then minus gamma h bar some x field, let's say. Okay. So I have a transverse field, and when I write a dot product, then I'll have a Ix with Hx operating on some state, and then there is a possibility of changing the state, because the Ix can be written in terms of I plus I minus. So depending on your initial state, you can go up by plus 1 or go down by, so go by plus 1 or minus 1. Okay. So so you can have a transition. So firstly, you need a transverse field for a transition, and also if you want to transit from some m prime to m, then this delta m has to be plus minus 1. Okay. Only those are allowed, because I plus can change it maximum by 1, I minus can also down maximum by 1. Okay. So those are the only transitions that are possible. And so obviously in this kind of situation, so from here you can have a transition up or down here, but plus half cannot go to minus 3 half. That's obvious, no? Because again, will write in advance. So in a somewhat longer form, write this at some point. So perhaps some of you will remember. So this goes as so with I plus, maybe there is no H bar. So there is a, so your state is if I plus acts on this state, then what do you get? You get something like I times I plus 1 minus m sub I minus 1, I forgot, plus 1. Yeah. Yeah. For the plus sign here, you get plus 1, and then this gives right. With this you recall. Likewise, if you had a minus sign here, so if a lowering operator acts on a state, then there is a minus sign here. So with a minus sign here, you will have a minus sign here and a minus sign here, right? So because of this, you can change state from m prime to m. So when you're trying to calculate expectation values, so on the left side you will have some m prime. So ultimately you will get the when you multiply from the left by I m prime, you will get non-zero value only when that m prime is m plus 1, if there's a I plus, right? So you get transitions only with plus minus 1 possibly. Okay. So yeah, and also by equating this energy, you usually write omega as 2 pi nu. In an experiment, it's not the angular frequency. When you have some RF source, you're applying some 100 megahertz or whatever, so it's nu. Okay, so the H bar cancels, and then you get omega is gamma H naught, and since you are often dealing with nu, you get nu as gamma by 2 pi times H naught. So what is interesting is also that you have actually looked at quantum mechanical problem. You have quantized energy levels, you have a Hamiltonian, and then you are saying there will be a resonance and so on. So there is H bar there in the problem. But in the final answer of what the resonance frequency is, the H bar has disappeared. Okay, so classical treatment of course has no H bar. Okay, so classical treatment also gives you the same answer. So your question of somewhat related to your question of what field should I apply to get a resonance. Well, you can apply any field you like, but then your observation frequency must be determined by this equation. Okay, so by now, research in nuclear physics and atomic physics is more than 100 years old. So different nuclei will have a, by the way, what is, so I'll rewrite it. So we got what? Nu as gamma by 2 pi H naught. Gamma is the gyromagnetic ratio. Often one also writes this as gamma bar H naught. Okay. Like H is whatever, and then H by 2 pi is written as H bar. Similarly, gamma is gyromagnetic ratio, gamma by 2 pi is written as gamma bar. And often in literature they might quote this value, because often you're dealing with what frequency do you get at a given field. So that multiplication factor is gamma bar. So this gamma bar is often quoted in megahertz per Tesla. So if you apply 1 Tesla field, the resonance is going to be at what frequency? That's what they will answer. Incidentally, all this applies to anything with a magnetic moment. We said nuclei, but it can be electron also. Okay, and if you do the experiment with electron, of course, the spin is only one possibility, half. So there's no 3 half, 5 half, and all. Nuclei, because it's a collection of particles, you can have any value. If you do this kind of experiment with electrons, then it is called ESR, electron spin resonance. So it's again a Zeeman splitting of the electron energy levels, and then you have some RF field. In that case, it's not really RF, it's not radio frequency, it's much higher because the value of gamma. So what is the expression for gamma for an electron?
E by 2. The charge.
So don't forget. Okay, there's a Landé G factor. There's a G. So G by 2m. Again, people use Gaussian MKS units interchangeably. In magnetism literature, still most of us continue to use Gaussian units because they are very convenient in many places. There is no mu naught, epsilon naught to worry about. And anyway, in high energy physics, ultimately people say H bar is 1, C is 1, everything is 1. So all that is incidental. So anyway, so this one is with Gaussian, and without the C is with MKS. But as I always mention in my course, for usual things, mass and length and energy, it's very easy to convert from MKS to CGS, right? Just there's some 10 power something, okay? Kilogram to gram 10 power 3, meter to centimeter something, ergs to joule to erg 10 power 7. Straightforward. Not so for electricity magnetism, because you have these mu naught, epsilon naught, which are there in the force law, right? Q1, Q2 by R square is the force. But if you're writing in MKS, then there's a 1 by 4 pi epsilon naught. Likewise, for the magnetic part, there's a mu naught. So conversion from MKS to Gaussian is not just some 10 power something, unfortunately. So charge of electron 1.6 10 power minus 19 coulomb. In Gaussian units, how much is it? Nobody will know. Almost. So there's a factor of C, speed of light, that will come in. It's some 4.8 10 minus 10 ESU, electrostatic unit. So that is also very vague. What is this electrostatic unit? So you need to, so most books will have older books, front cover or back cover, they'll have a page of what these are, how these are converted. So what I'm trying to tell you is that mass is okay, electron mass 9.1 10 minus 31 kg or 10 minus 28 gram, no problem. C is, so that's why the conversion is not, the gamma gyromagnetic ratio is G by 2m for MKS, but G by 2mc for Gaussian. But then the E is not just conversion by some 10 power something, there's a C which comes into it, speed of light. So
is it correct that in the US college system they are always using CGS unit, or most often?
yeah, it's true, most of the classic books, they have used Jackson, old version uses.
In the teaching also they are most commonly, or they are fine with?
Nowadays I don't know, I have not been there for 30 years, but yeah, always it used to be Gaussian, for magnetism at least Gaussian, because then you don't have to deal with this epsilon naught, mu naught. Unnecessary mess. The concept doesn't change. So, right. So you can. So okay, we can do this. Then you are happy with the MKS. So typical. So for electron there is unique gyromagnetic ratio. There is no confusion. Okay. 1.6 10 minus 19, 10 power minus 31 here, 2 and so on. You can calculate. Okay. Any nucleus, the nuclei is going to be different. Proton has a different mass, the G will be different, Lithium, again, number of protons, neutrons is different, spin is different, M is different. Different nuclei are going to have a different value of gyromagnetic ratio. So the resonance condition for different nuclei is going to be different. So one needs some list of gamma values for various nuclei. Okay, so all that research about what is the magnetic moment for this particular nucleus, all that research has been done, luckily. And so you have an available table of what is the gyromagnetic ratio of yttrium and copper. Again, you might have different isotopes. Okay, so for example, copper metal, as far as electrons are concerned, only one kind of electron, there is no confusion. But there are two isotopes for copper. There is a copper 63 and copper 65. And the natural abundance, if you mine copper from a mine and then purify, etc. I forget now, it's roughly 70-30, I forget which is which, but roughly 70% of it is copper 63 and remaining 30% is copper. So you take a copper metal piece, it will have some fraction, some 70%, 65 copper, remaining copper 63. Both are there. Okay. They will have different gyromagnetic, because this number is different. Number of neutrons is different. Okay. So they'll have different gyromagnetic ratio, different NMR signal. Frequency is different. So we have to be aware of all these things. So main point is that many things which will determine finally resonance, whether observed or not. And so you need a table of. So for example, you always write the nucleus with this thing on the left to indicate what is the number of protons plus neutrons in the nucleus. So you have 7 lithium, 89 yttrium, 63 copper, 65 copper, and so on. And so one must tabulate what is the gamma bar for each of them. And so when you're doing an experiment, you need to know this. So for example, this is some 42, it's always megahertz per Tesla, because then you get numbers which are like, of the order of 1 or 10 or so. So it's easy to remember. So proton is like 42 megahertz per Tesla, lithium is like 17 megahertz per Tesla, this is like 2.2 megahertz per Tesla, this is some 10, 11 megahertz per Tesla, and so on. Some nuclei may not have a moment also. Okay, prominent one, which is there in most of the oxides we measure, is 16 oxygen. It has 8 neutrons, 8 protons, and there are again atomic physics. There are rules to determine what the ground state is. Both neutrons and protons have spin half. This collective object with 16 particles, neutron and proton. What is the net spin angular momentum? Anybody know what it is for 16 oxygen? I mean, the NMR people will know, but the others, 0. So it's there in so many oxides. We are measuring so many oxides. The most abundant isotope of oxygen, almost 99 point some %, is 16 oxygen, the oxygen that we breathe. It is 60, this isotope. Unfortunately, it has no magnetic moment. If there's no magnetic moment, there's no issue of resonance or anything.
Because it is have even physics.
It's a even, yes. Yeah. So if you remember some nuclear physics and what energy levels you'll get, so all the physics you will learn. Sometimes you get the feeling that the physics I learn in classroom in courses is not useful for research. I mean, I keep trying to keep telling that idea is completely wrong. Whatever you learn in class is directly applicable in research. You need to know even simple things, right? So always useful. So, for example, this even nucleus, oxygen, has no nuclear moment. So you cannot measure any resonance. However, there's another isotope with one more neutron that has a magnetic moment, and so you can use that to do your resonance experiment, nuclear resonance. Unfortunately, it is not naturally abundant. In natural form, I don't even remember, it's like 0.01% or something like that. So again, issue is, can you measure? In principle, yes, there is some oxygen 17. In practice, sensitivity will not be enough. So how can you now still, sometimes you really want to measure the oxygen because it's located at such a position that you are trying to probe the magnetism from some copper or something else, and this is really a good probe. So what do you do?
High magnetic field. High magnetic field.
But if it is abundance is so low, you cannot go to 100 Tesla. You know, from 1 Tesla you can take it to 10 Tesla. So yeah, this is one way that you try to increase the field to improve the sensitivity. But not always possible. You have the same magnet. You are measuring other things. Now, what else can you increase? Sort of. You enrich. So you have commercially available cylinders of oxygen 70, pure oxygen 70, which costs lakhs of rupees. But if you have a critical experiment that you want to do, so you buy a cylinder which is
We
pure.
want very little amount of oxygen 70. We will not use it will be not very costly. Is it costly?
One small cylinder like this costs thousands of euros.
Oh.
So lakhs of rupees. So in comparison, if you take a huge cylinder, you have seen the departments, big cylinders lying around. So that typically costs 5,000, 6,000, something like that. Good high purity, huh? And big cylinder, like this high. Some 5,000-6,000 rupees. Compare that with oxygen 17, this tiny one, it's called a lecture bottle. Because you want to demonstrate that the name is lecture bottle, it's tiny, about this size. In terms of volume also, it may be, I don't know, 1/20th, 1/50th of this big one. It costs several thousands of euros, dollars, whatever, so lakhs of rupees. So, but people do that, you buy that and you're preparing your sample and you're using oxides and you have a chemical process such that instead of this, you insert oxygen 17 in your sample. So, in your usual sample, you had maybe 0.01%, I don't know, whatever is the natural abundance. As you say, bombard with neutrons, sort of. Somebody has done that and purified oxygen 17. You take that and then use that in preparation of your sample. So you insert oxygen 17 and that has a magnetic moment and then you can do experiments. Again, not easy, so it is, price-wise it's little forbidding. And even after that, you might get maybe 2%. All the oxygen you may not be able to replace from your sample, only some. So whatever you can manage, then you need long experiments, you need sensitive electronics and high fields if possible. So yeah, so you are limited by several things. Firstly, it has to have a magnetic moment. In some cases they don't, then there's nothing you can do except if you have this kind of possibility. But then there are some others which are fantastic. So proton, all chemists, they use proton NMR. Okay. So again, maybe a bit of a digression. Proton is like some 42 megahertz per Tesla. So, physicists think of magnetic field in terms of Tesla. You'll say, oh, I have a 9.4 Tesla magnet. Okay. Somebody else has 8 Tesla magnet, 9 Tesla, 7 Tesla, right? But when these companies selling NMR spectrometers, they'll sell you a magnet, it's a 400 megahertz magnet. Okay? The meaning is that magnet is not 400 megahertz. If you look for the proton resonance in there, it will appear at 400 megahertz. So, roughly speaking, so they'll quote, 100 megahertz NMR spectrometer or 400 megahertz, whatever. Okay, so for example, in my lab we have approximately 9.4 Tesla magnet. That is actually a 400 megahertz. It means if you did proton NMR in there, the resonance would appear at about 400 megahertz. So because you have 42 megahertz per Tesla, multiply by 9.4 and you get about 400. Okay. So the highest in the institute that we have is, I was trying to remember the field, huh? So it's actually 650 megahertz. So the highest in the institute is a 650 megahertz.
750.
It's 750, you may be right.
It's high.
You told that before.
I told that earlier. Please check. So it's in SAFE, it's a central facility. Okay, so I don't remember exactly, 650, 750. Maybe 750. So just check, it's some 16 Tesla or so. Okay, so anyway, so worldwide, what is the highest? Yeah, they have gigahertz, so 1000 megahertz ka bhi hai. But remember, there's a challenge for engineering also. You have to have high field persistent magnets. 750, you check? Yeah, good, thank you. So 750. Calculate the field. How much is the field? Divide by about proton gamma is how much? 42 point something?
Something.
Check what is the proton gyromagnetic ratio also. So what is gamma for 1H? Gamma bar is what we are looking at. You know, I remember 42 megahertz per Tesla, but precise value is maybe 42 point something. Or you can just check. Actually, if you do 400, if you do 400 by 9.4, that will tell you. 42.5 something. Right. In fact, 400, because this I know ours is 400, I know our field is like 9.39 something.
42.55.
Some 42.5 something. Right. So this 750 gives how much field?
17.64.
Okay, so I was wrong. So from 17.6 Tesla.
But maybe they are not operated at the top.
No, they are.
They are operated
Of course,
at
it's fixed field.
It's fixed.
Okay.
They are operated at the full field. Yes. And so that's a separate topic. These are superconducting magnets, of course. Persistent magnets. So no power supply anymore. You know, current is circulating, and you just keep it cold enough. Keep it at 4.2 Kelvin. So that one every 3 months, you have to fill in about. I think that one you have to fill in about 300 liters of liquid helium. That's a big magnet, no? So.
And how much producibility we have in ID normal liquid helium plant?
Now we have a new plant.
Per day around 10.
Much more. I'll tell you. So if you go, our so-called infinity corridor is actually not infinite. It ends in mechanical. So there's the liquid nitrogen, liquid helium plant at that end. So we have one in the department which is down for a few years. So that itself was 30 liters per hour.
Per hour.
Yes. So this one is much bigger. So
In T-lab.
it's in mechanical engineering at the end of the.
T-lab kind of.
What lab?
At the end.
At the end of the corridor.
You go straight and then at the
Sorry,
end.
I don't know which direction I'm pointing correctly, but yeah.
I know it's mentioned in T-lab.
T-lab.
No, liquefaction lab. It takes
Mechanical engineering end, the infinity corridor. You just if you go in first, you'll get the liquid nitrogen plant. So if you have to get liquid nitrogen for our lab, you also sometimes maybe are doing liquid nitrogen or not.
Yeah,
No,
we
no,
have
so
thermal
that's-
deposition machine we have and
Yeah.
we pull down that particular
Yeah,
machine.
so that's where you get liquid nitrogen. If you go further inside in left, then there's a helium liquefier also.
Yeah, I saw that.
You've seen that?
Yeah.
Okay. That's a new one.
Yeah.
That was installed last April or so. Cost is also enormous. Guess what the cost of that helium? We are digressing, but it's okay. This is general. So, what the cost of that plant was?
What is one?
Crores. That's easy, you know. Our lab magnets are crores.
our lab has 4 crore.
Lab magnet, that's a field stream magnet, the whole thing is like 4 or 5 crores. Crores.
How much?
How many crores? It's close to 25, 30 crores.
30 crore.
Yeah. So we of course recover all the helium that boils off.
And that fund is covered by one body like DST body or there are multiple body crammed together.
Now we are getting into a different discussion. Yeah. But this is all government money. It's all government money. Yeah. You know, we had this special money because IIT Bombay is an institute of eminence. Okay, so we had some special money from the government for many years. So it is from that fund
Because
that.
my idea is asking to whenever the money is coming up, the accessibility will be changed. Like it is not the IT Bombay facility current. Maybe in the future some other institution access to take it some liquid helium.
Absolutely. So you're talking about some administrative thing. So in fact, that is the picture. That this helium is available for everybody, you have to pay for it. You have to pay for it. It's not free. There's huge maintenance cost of all this, huge starting base cost. So again, since you brought this topic, if you are recovering all the liquid helium, right? Helium is always boiling. You know, inside 4.2 K, outside 300 K. So it's always boiling. So gas is coming out. You don't want to let it go. So you might have seen recovery lines. It recovers, gets into a big gas bag. Then it's compressed back into cylinder. Okay, but it is not pure, fully pure that time. No, it's not like 99.99 pure. Right? Some 95, 98, 99, that sort of purity. If you are recovering all the gas at this 98, 99% purity and returning to them, then the cost is about 15,000 rupees per 100 liters, which is very low. If you buy in open market, you pay more than 2 lakh for 100 liters. Okay. So outsider, if they can buy, yeah, of course, they give.
Centralized system.
So we are also paying.
We are also paying, yeah, yeah.
Getting-
We are paying a reduced cost because of, yeah, because ek to internal there's a special cost, and then we are returning the gas. Okay, so yeah, so there are various challenges in doing these experiments. Agreed, bigger the field, the better the sensitivity. Not always, but yeah, usually you want higher fields. The biggest we have here is this one. These are all persistent magnets. So they are superconducting magnets, you know, in a liquid helium bath. In the first time they are installed, engineer comes and, you know, sets up a current, and then if all goes well, that should remain forever. Right? Superconductors, the decay is over, I don't know, 10 power something, what astronomical lifetimes. Okay, so it should be there forever with very little drift. Yeah, so in practice you have these situations. Then yeah, we digest, but that's okay. That's the whole purpose of this, so that, you know, we also touch various other issues related to the actual experiment. Okay, so now, yeah, so what did we sort of, what point did we come to? We'll have these equally spaced energy levels, and you can apply a field which is perpendicular to the DC field, and then enable transition between various levels. And it is basically determined by what the gyromagnetic ratio is for that nucleus, because for a given field, the gyromagnetic ratio will determine what frequency you observe the resonance. Okay? And of course, as we said, the transition is possible only between neighboring levels.
So since it is a non-destructive technique,
Yes.
can we go to very, very high fields also and it will not affect the sample? Means basically nothing will happen at extremely high fields also.
Probably not, yeah. Probably not affect. I mean,
That will depend on sample to sample.
Yeah.
Sample has a expansion or
with magnetic field, you might have. I mean, it's not obvious. I agree. But for example, so NMR people have done in, so Grenoble there's a high field lab. It's not persistent magnets there, because you cannot get at 40 Tesla, 50 Tesla, then some combination of persistent and other magnets. But so there they have done at fields of 40, 50 Tesla, surely 20, 30 Tesla. Whether it destroys the sample, at least those ones, you know, biological samples, human beings we don't know. But 8, 10 Tesla is okay, because MRI, you know this technique called MRI, magnetic resonance imaging. It is nuclear magnetic resonance. Okay, more sophisticated. It's not a DC field. There's a field gradient. It's not a spatially uniform field. There's a field gradient, and then there's lot of software and, you know, a lot of engineering. But it's nuclear magnetic resonance. The name probably has been given as MRI because common man is afraid of the word nuclear, because you think there's going to be radiation, atom bomb, you know, these kind of things. So to that extent, it is non-destructive. You know, you do biological samples, you do NMR, at least up to 8, 10 Tesla.
They are not more than that. MRI.
MRI,
Have you heard? I haven't.
I don't know, but
There are chances of getting ionized also.
No.
If fields are high.
Is it?
5 Tesla though is common. Yeah.
No, it's very.
1, 3, 4, 5 Tesla superconducting magnet. So those are, watch out. There are other challenges also. It needs to be horizontal magnet.
Huh.
You know, I will not go this way in the magnet. The sample you can put anyway. So it needs to be horizontal, and whole human being has to go in. So the bore has to be like this big. So all kinds of different challenges.
अरे उनका काम चल जाता होगा
How
अब
much?
तक तो I mean, these are all tested, and you're not inside for like days, no? Sample is inside for days. You are inside for I don't know,
15 minutes.
something
less
like
than
that.
15.
Hour, I
Okay.
mean, of the order of उतना भी नहीं है, 15 minutes, 20
15
minutes.
minutes.
So at least in that time, I don't think there is damage. At 100 Tesla, what would happen? I don't know. I don't think it's big enough.
It is in some kind of theoretical limit to that extent. Okay, we want not up to high. That
Yeah.
much.
Theoretical limit for what?
For persistent magnets and magnetic.
Consistent magnetic.
For electronic magnets, sir, we cannot go like 4-5 Teslas.
So iron magnet, okay,
Hmm.
non-superconducting magnet. It depends on saturation magnetization of what material you use.
And then for
So-
the persistent one, what is
So
limit?
there the limit is, so iron magnet, electromagnet, you know electromagnet, you know these big ones are there, so you have some coil and then some former, so it depends on the iron that you use. So 2.2 Tesla, that's the limit.
Hmm.
And you need cooling, water cooling, because I square R heating is always there. Then this neodymium iron boron, you know, where now China has all the control over rare earths all over the world. You know, it's China is holding the trump card in that. Trump is talking, but China is holding the trump card, right? So all the rare earth control is with China. So neodymium and all that. So neodymium iron boron magnets are the strongest magnets, permanent magnets. So there you can generate again still Tesla. But by the way, those magnets are useful. Yeah. We'll also stop in a short while. Those magnets are used in all, you know, automobiles, motors, in film for small, also in mobiles, you know, just everywhere. And just one country seems to have control over that. So anyway, so
Sir, but if
the limit.
We are applying an external field, right?
Yeah.
Magnetic field. It will polarize the material. It will
Yep.
destroy. It will destroy the magnetic phase of the system. Right?
So magnetic phase, yeah, it depends on the material. What is the, how does the magnetization vary as a function of field? Yeah, so you might be exploring different regions of the phase diagram. Yeah. So
No, I mean,
whether you can come back to, whether it's irreversible, usually what has been looked at, it has been always reversible. Yeah.
Well, let's say we want to study nail phase or
Yeah.
crystal liquid.
Yeah.
If you apply
Huh.
strong in the magnetic
Yeah.
field, it will polarize the material, right?
Polarized means
I mean, it will,
Polarized
let's
means
say,
all things are in that
magnetic
direction.
Ha.
That's
So it,
your
so there's a
property of the
there-
material.
there's an interplay of what the internal interactions are and what the effect of the field is.
but always we can destroy that phase by temperature effect or not.
but we want
Temperature effect, also field
We
effect.
destroy that particular.
Then you don't go to high field. Yeah.
But we want to study, like, let's say I want to check what is the magnetic ground state
Huh.
of this material.
Ground state means zero magnetic field. Zero temperature, zero field.
Okay, we are from theory, so.
Yeah.
So let's say I want to check if it's a QSL or not.
Yeah.
And maybe this NMR is in there.
Yeah.
Okay?
Yeah.
And if now I apply a magnetic field,
Yeah.
we will get that. I mean, if it's QSL, I don't know what are the signature, but if you apply a magnetic field, the spins will get polarized to that magnetic field.
So
A little bit.
no. So quantum spin liquid, for example, then the exchange coupling is of the order of, let's say, I don't know, 50 Kelvin, the J. Then you need to apply 50 Tesla to overcome that.
So that, I mean, that was the question. Like,
Correct.
as you were saying.
There's always an interplay between what the strength of the coupling is to what the field that you can apply. So there's an interplay of all these. Yeah. But it will not be irreversible. You may not be able to study what you want, but you bring back the field, and the system should come back to the old state.
Probably this question is also regarding the structural integrity of the sample, like whether it gets, yeah, like whether it gets destroyed.
Whether it gets destroyed, yeah. So usually, so there are also people who do magnetization measurements in high fields. So you get pulsed magnetic fields. It's not easy to get constant magnetic field at like 100 Tesla, but you can do pulsed magnetic fields. What they do is you have a huge capacitor bank, charge up the capacitors, okay, and then through a tiny coil, discharge in one shot. So you'll get 100 Tesla for milliseconds and then down. And in that short period, you measure the magnetization. So you can do magnetization with high field like this. So structural integrity, at least from what we see in literature, it comes back to its old state. So
in your lab, some kind of temperature control system like cryogenic also have.
yeah. You want to measure as a function of temperature. Yeah. So maybe I continue next time. What we want to do next is, so what's the phenomenon of resonance for a, let's say, spin half system? Plus half, minus half. You know, in order to cause a transition, you need some, for a theory, you need some matrix element, okay, which will allow from one state to other. And the transition rate, what's the probability that you get a transition? It's given by Fermi-Golden rule. All what you learn in so-called theory classes now, everything is useful in experiment. Okay, don't think that once you are doing experiment, theory you can throw away. You cannot. So the transition probability, whatever you call it, W or something. So we'll anyway continue next time. It depends on 2 pi by h bar square of the matrix element, and then of course you need a delta function, which is the energy that you're externally providing must match this energy. Okay, so and then equilibrium, what will happen? So, so there are a couple of things. One is, in order to cause transition between levels, you need some matrix element connecting that. Okay, so for example, we saw the AC field that you have will provide such a situation. Okay, but all these nuclear spins are also there in a reservoir, right? They're in a bar. So one question, I have nuclear other magnetic moments, okay? If I don't apply a field, then there is, there are no two states, but then there is equal population of plus half and minus half. When I apply a field, then some should get polarized, right? But then there must be some connection with the reservoir.
But ideally they are not equal at a particular temperature.
So how that comes about, this is what we want to see next. Yeah? I mean, you will, if you have a nuclear spin system which has almost no connection with the so-called lattice, the reservoir bath, you will never be able to magnetize it. Because in order to magnetize, it has to get you apply a magnet DC field, okay? And then, so now you must have transition. But then something else should take up that energy. Well, whatever energy change is taking place, some other agency should take that up. For that, some connection should be there. So this goes by the name generically your spin system, and this other thing goes by the name of lattice. So this was actually one first challenge for observation of NMR, I don't know, 70 years, 80 years back, that if you take a sample where there is very weak coupling between the lattice, first you are not able to polarize those nuclear spins. Actually, same for electron spins also, but somehow the connections are good, the couplings are good, so you are able to get it. But this was the first challenge, that the coupling between the spins and the bath, spins and the lattice, if it is very weak, to first apply a field and cause a population difference is itself a challenge. Then to have the AC field and cause resonance is the next step. Okay. So anyway, next time we'll continue from here. So for these simple spin half system, if you take a transition rate from plus to minus as some W, and then how does the population of each level change with time? So we will see that. And then if you apply AC field also, then what happens? And we go on from there. Yeah. So the thing is now I have to go to IIT Kanpur for a PhD